Good morning, ladies and gentlemen. My name is Mitchell Goldie. I'm joined here by Danny Nguyen, Owen Schneider, and our technical director, Mr. Robert Corvesi. We are Team IGT, here to present to you our capstone project, the Headless Terminal. Lottery terminals worldwide are made with touch and screen interfaces with which the user or retailer can interact with the terminal to produce a wager, print a ticket, perform other functions. The purpose of our project was to explore the feasibility of making a terminal without this touch screen, i.e. a headless terminal. And we were essentially tasked with designing such a system from the ground up. Our best anticipated outcome for this project then would be a fully functional prototype of such a system, which is capable of receiving and processing these voice commands, translating them into appropriate terminal functions, and employing a voice assistant to help the user more quickly, efficiently, and pleasantly place these wagers and perform other functions. So why a headless terminal? Well, it could have significant impact for IGT, as a single touchscreen can be quite expensive, costing upwards of $200. Eliminating the need for such a touchscreen could allow IGT to make significantly more profit per unit that they sell of these terminals. Additionally, a headless terminal like this would be more in line, better serve the needs of IGT's visually impaired customer base. Currently, IGT sells terminals which have a touchscreen that works in conjunction with simple text-to-speech commands that help visually impaired users navigate the screen. Our solution, however, would be more robust and would better reflect the current state of voice recognition technology today. This is a simple block diagram of kind of our current hardware prototype. We have the Raspberry Pi, which is the computer that we're implementing our software design on. We have a microphone and speaker for audio in and out, a printer for printing the tickets, and an LED indicator that turns on when the terminal is ready to listen to the speaker.
So one of the most important documents we worked on this semester was the high-level design document. This document details the features that our terminal must provide in order for us to meet specific design requirements. These requirements include printing a lottery ticket in under 4 seconds, as well as accurate speech recognition. Furthermore, detailed is the scope of the project, which details the functionality that our terminal must have upon the completion of the project, as well as how current and future versions of our system architecture can be created. Then there are the risks and constraints to our project, which limit our design decisions in order for us to fully encapsulate the ideas that IGT has for this lottery terminal. Overall, the high-level design details how this project is to be carried out and what IGT is envisioning from this lottery terminal. So these next documents stem from the ideas of the high-level design document. On the right, you can see an example of activity diagram. Our activity diagrams are essentially flowcharts which describe the flow of interactions between the user and terminal, specifically placing lottery wagers, handling system errors, and user login and settings. The use case goes into further depth, specifically what the user should be saying at specific junctions and how the terminal should be responding and reacting to different user inputs. The speech recognizer we decided to use for this project is called Pocket Sphinx. It is open source and free for use in an offline setting, which was one of the constraints for our project. One of the most difficult parts of this project was training the recognizer to rise above its initial accuracy rating. Initially, it was at about 50%, and this can be attributed to many different factors, such as CPU hardware limitations, as well as ambient noises affecting the quality of audio going into our microphones. We identified many different things, however, to train our recognizer to become more accurate. The first thing we adjusted was the acoustic model. This helps the recognizer understand which audio samples go to what words. Then the language model helps it understand what words are likely to come after other words in order to construct full sentences. And then finally, we adjusted the dictionary from its default 130,000 words to 50 words, improving both the recognition accuracy as well as the runtime of Pocket Sphinx. After making all these adjustments, our accuracy went up to about 75%, with room for future improvements through the course of the next semester.
Our final key technical accomplishment for this project was creating a hardware prototype. Our hardware prototype has 4 main components: the Raspberry Pi 3, the new Howdy USB microphone, the Racono mini speaker, and the Raspberry Pi X350 soundboard. We chose to use the Raspberry Pi 3 for our project for its prototyping flexibility, allowing us to interchange different microphones and speakers to test their viability. And after extensive testing, we also chose to use the new Howdy USB microphone, for its exceptional sound quality and with respect to its affordability. Similarly, we chose the Racono mini speaker, again for its exceptional sound quality, compared to its small size, allowing our digital assistant to be heard by the user at fair distances. And then finally, our X350 soundboard acts as an audio to digital converter, allowing our analog input signal to be understood by the Raspberry Pi. Going into the next phase of our Capstone project, our main goal is to implement the entire functionality of our terminal that we spent this semester designing. Our first step towards this accomplishment is to improve our speech-to-text performance. As Danny mentioned before, our speech-to-text performance falls at about a 75% accuracy percentage. We need this accuracy percentage to be raised above 95% to ensure that we have functional reliability. Using our hardware prototype as a framework, we will also be designing and implementing a printed circuit board that will house all of our terminal's embedded electrical components. With this printed circuit board, we will also be continuing to test and improve our microphone performance using different signal processing and filtering techniques to ensure they have the most clear and concise input signal going into our terminal. We will also be, if time allows us, designing and constructing a functionally viable and visually pleasing enclosure that will house all of our embedded components, finalizing our headless terminal. With that being said, I would like to thank everyone for your continued support and the support of this project and the program as a whole. Thank you.